Okay, we're going to start with 2.9. It says the car goes from plus 30 meters per second, so that's an initial velocity of a plus 30 meters per second, and to a plus 60 meters per second, so the final velocity equals a plus 60 meters per second, still going in the same direction, it looks like. And in 3 seconds, the time is 3 seconds. What's the acceleration rate? So we're going to use the equation A equals Vf minus Vi over t. So that would equal final velocity is 60 minus initial velocity is 30 divided by the change in time is 3. So that would be 30 divided by 3, and we have an acceleration rate of a plus 10 meters per second squared. This would mean this car was speeding up both times, because at the beginning the initial velocity was positive and so is the acceleration rate, and at the end the final velocity is positive and so is the acceleration rate. And when they're the same signs, it means it's speeding up. Okay, let's look at 2.10. Again, we have an initial velocity of a plus 80 meters per second, so it's going pretty fast to the right. But then its final velocity is a negative 20 meters per second. So that means now it's going to the left. So somewhere along the line, it must have slowed down, stopped, turned around, and speeding up in the other direction, it looks like. So the time that it does this is in 5 seconds. Again, we're going to use acceleration equals Vf minus Vi over t. And so my final velocity was a negative 20 minus a starting velocity was 80. And we're going to divide that by 5 seconds. So that a minus 20 minus an 80 is a negative 100 divided by 5 gives me a negative 20 meters per second squared is the acceleration rate. So the acceleration vector is to the left. It's a negative, which means at the beginning, when your initial velocity was positive going to the right, that means we were slowing down. And then eventually it stopped, turned around, and started going back the other way. And now the final velocity was negative, and so was the acceleration. So we'd be speeding up there in the end. All right, let's do 2.11. Okay, it says from rest. All right, that's actually information. The initial velocity equals 0. You should write that down. A ball rolls down an incline at a constant acceleration, A, is a negative 2.00 meters per second squared. Okay, question A. What is the velocity of the ball after 8.5 seconds? So we have another thing. We have time equals 8.5 seconds, and we're trying to find out Vf. That's what we want. So we need an equation that has all of these variables in it. We'll notice that distance is not anywhere in this problem, so we don't want a D equation. So we're going to use that first equation again, the acceleration, the one, but we're going to solve it for Vf. So Vf equals Vi plus At, and Vi is 0, so this thing can cancel out, so that's nice. So Vf is going to equal our acceleration, negative 2, times the time, 8.5, and we should get a final velocity of like negative 17 meters per second. There's our final velocity. There's a part B to this. Part B says, how far did it roll? So how far did it roll? That we actually need the displacement now. So how far did it roll on that side? So we're going to use D equals VIT plus 1/2 AT squared is the displacement formula we can use. Initial velocity was still 0, so this whole term goes away, so that's always nice. When initial velocity is 0 or it starts from rest, there's a whole term in these equations that'll go away. So now we have D equals 1/2 AT squared, so I could do 1/2 times the acceleration was a negative 2 times the time, 8.5 squared. And if I do that outright, I get like negative 72.3 meters. I'm not really looking at my sig figs here, so I don't know. Maybe I should have 2 sig figs or something like that in there. Okay, That's 211. Let's do 212. 212. It says a car is traveling at 88 kilometers per hour. All right, so that is an initial velocity, but unfortunately, sometimes I'm a mean teacher, and I do not give it to you in the MKS units. Everything needs to be in MKS units before you do a problem. So before we even read any more in this problem, let's write down 88 kilometers over hour, and let's convert that to meters per second. So I have 1 kilometer is 1,000 meters, and I have 1 hour on the top, and that is 3,600 seconds. Hopefully you can do that in one step. You could do 1 hour is 60 minutes, but then you do 1 minute is 60 seconds, and 60 times 60 is 3,600. So it's just nicer to do it that way. Okay, so I take 88, and I have 1,000 up here on the top and 3,600 on the bottom. So really all I need to do is take 88 divided by 3.6. And so that's an initial velocity of like 24.4 meters per second. Now, here's something important to remember. Never do this math again. Never do this math again. If I give some velocity in kilometers per hour, you need to put it in meters per second. Just try to remember. To do that, you divide by 3.6. That's how you go from kilometers per hour to meters per second. So kind of memorize some of these little shortcuts once you know the dimensional analysis conversion. Just take a kilometers per hour, divide by 3.6, and you'll be in meters per second. Okay, let's look at this problem. We have an initial velocity of 24.4. It undergoes an acceleration of a negative 8.0 meters per second squared. And the first problem says, how long does it take for the car to stop? So we're looking for a time. And we actually got one more piece of information. There's a VF. The VF is 0. It stops. So the final velocity is 0. And we need time. Okay, so how do we do that? Well, we could do the acceleration equation. Acceleration equation equals VF minus VI divided by t. But we want to solve for t, so t would equal VF minus VI over A. So we could do it that way. So I'm going to have 0 minus the initial velocity, 24.4, and I'm going to divide it by a negative 8, and that'll be about 3.1 seconds. That's about how much time it's going to take for it to come to a stop. There is a part B, and part B says, how far does the car move during this time? How far does it go during this time? So we have D equals VIT plus 1/2 AT squared, and is the one I could use. I could do a couple different problems here. So let's look at it both ways. So if I do it this way, I'm going to take my initial velocity, 24.4. I'm going to take it times the time, which is 3.1, plus 1/2 times the acceleration, negative 8, times the 3.1 squared. Okay, and if I solve that problem, you do that, you should get around like 37 meters. Now, just to show you that there's other ways to do these problems sometimes, I could have, because I actually knew the time in part A, I could go ahead and use the time in part B. But if I didn't have the time, what if I did question B before I did question A? I could have actually still figured this out because I could have used the third equation we have, VF squared equals VI squared plus 2AD. So that would be VF squared minus VI squared all over 2A would equal my D. And I could plug everything in. I could put 0 minus the 24.4 squared divided by the 2 and divided by the negative 8, and I would have also got a displacement there, and it'd been 37 meters. So there are multiple ways you can do some of these problems. Okay, one more problem. And there's a little thing in the book there that says that whenever we're doing anything that's free falling, anything that we're dropping or we're throwing up in the air, then we automatically know what the acceleration is. We automatically know what it is. It's going to be, the acceleration is going to be what we also call g. So whenever we're doing one of these types of problems, we call them gravity problems, we actually know what the acceleration is. It's going to be g, and g on the Earth is a negative 9.81 meters per second squared. So whenever we have anything that we're falling or dropping or whatever, you should know that you actually already know something about the problem. You know what the acceleration rate is. It's a negative 9.81 meters per second squared. All right, let's look at 2.13 is the last problem we want to do right here. 2.13. It says a cat with an initial velocity of negative 13 meters per second. So that's VI. Negative, whoops, that's messed up. Negative 13 meters per second is my initial velocity. Falls for another 14 seconds. So it's going to fall for 14 seconds. Total time equals 14 seconds. And the question, it's falling. So right now we can write our acceleration rate also, negative 9.81 meters per second squared. Okay. How far did it fall during just the last 3 seconds? Just the last 3 seconds. Okay, so what we could do is we could say, and it falls from, it has an initial velocity of negative 13. So we could use d equals VI t plus 1/2 at squared. Now, if we do this, if we use this equation and we put in negative 13 in for our initial velocity, and we put in like 14 for our time, okay, that will tell us how far we fell during 14 seconds. If we put in 3 in for our time, this is what a lot of students will be tricked by this. They'll say, well, I just want to know how far it fell during 3 seconds. So I can put 3 in for time, but that's not going to be right. That's going to be how far it fell during the first 3 seconds if I put the time in there as 3. So what I want to do is I want to actually solve this with 14 seconds, and then I can solve it again for 11 seconds. So I'm going to solve this d at 14 seconds, and then I'm going to solve how far it fell during 11 seconds. And then all I have to do is subtract those two. Okay, so this one's going to be negative 13 times 14 plus 1/2 times negative 9.81 times 14 squared. This one will be a negative 13 times 11 plus 1/2 times negative 9.81 times 11 squared. And I'm going to subtract those two. The first one for 14 seconds is going to fall a lot farther than it does for the 11 seconds. So in the last 3 seconds, it will be like a negative 407 meters. We need to put negative because it's falling downwards. So hopefully you understood that. A lot of people get tricked by those problems and just try to throw a 3 in for the time. That would just be how far it fell during the first 3 seconds. And that's not nearly as far as it's going to fall during the last 3 seconds because it's going a whole lot faster in the last 3 seconds than it was in the first 3 seconds. Okay, so that's 2.9 through 2.13. Hopefully that'll help you understand some of these problems, and you'll be able to do the rest of the catastrophe problems.